Thanks everybody for coming. So today, I'd like to share with you a few thoughts that engineers and scientists have on diamond. We all may be familiar with a statement that diamonds are girls' best friends, but what I'd like to convince you actually, they are not only girls' best friends, but actually engineers' best friends. And especially scientists and engineers like myself are very much excited about the diamond because of wonderful properties that it has and that can solve many interesting problems. For example, it can enable secure communication over long distance. It can advance computation via quantum computation. And also, it's an interesting material that can enable breakthroughs in the medical sciences, especially sensing. Also biocompatible material. It's chemically inert, so it's good for industrial applications as well. But what I'd like to start first, maybe just having audience say a few words that you guys know about diamond. What are the properties of diamond that you guys are familiar with? Just shout. Hard is one, excellent. Anything else? Which one is? Hardest natural material, it's excellent. Any other thoughts? Shiny, hard, shiny. Good, so sparkles. Somebody said sparkles? Excellent. So diamond is hard. It's actually one of the hardest materials, as young man in the front mentioned, and it's used to cut many other materials. For example, here's an example of diamond scribe that you can use to cut glass, but actually you can scale this up and use bigger pieces of diamond. This is industrial diamond that then gets mounted on a big drill bits that oil industry uses to cut huge holes into earth crust. So that's diamond's hardness is explored. We'll come back to shyness and sparkliness in a few moments, but before we go there, I actually like to get a volunteer to help me discover another property of diamonds. Anybody? Okay, well, please come up here. Want to come here? Okay, so what is your name?
Andrew.
Andrew. Where are you from, Andrew?
Framingham.
Framingham, Massachusetts. Excellent. Did you enjoy the snow? Are you happy it's over?
Yeah.
He says, yeah. Okay. Then Andrew will give you some ice because you like snow so much. Okay, and I'd like you to take a piece of this diamond, hold it like this, bring it to the ice, and tell me what happens. Say it nice and loud so everybody can hear you. It melts. Did your fingers get really, really cold? Really fast? Is it amazing? Okay, good. Thanks, Andrew. Please give it a hand for Andrew from Framingham. All right. He really likes this. Excellent. Okay. So what Andrew just helped us discover is the fact that diamond is the best thermal conductor. Okay? So basically what has happened, and you can try this experiment downstairs. We have many talented students, including my student Anna, who is in the audience, who can show you this firsthand, that heat from your fingers is channeled to this very sharp edge and melts the ice on the spot. But in fact, in that industry, like people who make these chips, the microelectronics industry have discovered this, and for example, diamond is now being explored as a material for heat spreading so that your computers don't heat up so much. So that's nice application of diamond that goes beyond shininess and sparkliness. But let's look at the sparkliness a bit again. So diamond sparkle, and here I have not quite diamond. This is zirconia. It has very similar properties to diamond. I don't know if you guys can see the sparkles as we're twisted. So the reason why diamond sparkle is because diamond is very good at bending light. So when I point this to you, light from this light source gets into the diamond and gets reflected and comes back to you. Okay? And diamonds are cut in such a way to achieve this. In fact, diamonds can bend light beams much more effective than water or glass. And that's a property that's used in jewelry to make very nice and sparkly diamond rings. But also, another nice property of diamond is that it can disperse light. So we know that white light, the light that we are using is white light, consists of many different colors. Diamond has nice property to actually separate this light into its colors. And that's what gives it extra sparkliness. All right, so now that we understand that there is so many different beautiful properties of diamond, what are diamonds made of? What gives this material such unique properties? Anybody knows? Diamond is a mineral, but what is it? What is it made of? Okay, how about you? Yes? Coal. It's a very interesting point. Diamond is not made of coal, but coal is its sibling. It's like younger or older brother. Anybody else wants to give it a shot? Carbon. Okay. So diamond is made of carbon. Excellent. And what else is made of carbon is coal, right? And what else is made of carbon is graphite. This young man knows all the answers. Excellent. Okay. Diamond is also made of graphite. So how come that diamond, graphite, and coal all have the same, they're made of the same material, the same ingredients, but they actually have very different properties. So that shows you that when nature cooks these different materials, it's not just enough to use atoms to use these ingredients, but you need to know how to cook them, how to prepare these materials. So basically, diamond has carbon atoms packed very, very densely, okay, in this crystalline lattice that's shown above. Actually, here is an example of such a lattice. So here we have, let's ignore the blue guy for the moment. We have carbon atoms that are very tightly packed in a lattice, whereas graphite, on the other hand, consists of layers of carbon that are reasonably well packed, but then these layers are separated for quite some distance, okay? And in fact, downstairs you can explore some demos that show you how you can separate each of these individual layers into sheets that's called graphene. That's actually won Nobel Prize a few years ago. All right, so this is excellent. We know what carbon is made of, diamond is made of, it's made of carbon. We know it has unique properties, but we really don't want to spend a lot of time digging for it, right? As if you ever played Minecraft like my son does, yeah? We all know diamond is very, very rare, right? Very rare. So if scientists and engineers want to make devices out of diamond, well, they certainly don't want to dig in the mines for long times. We would like to actually make them in a lab, okay? So the question is, can we make diamonds in a lab? And the answer is yes. Otherwise, I wouldn't be standing here. Though a lot of actually nice research in diamond technology has been done with natural diamonds before people figure out how to make nice quality diamonds themselves. So first approach that actually is used quite a bit is so-called high pressure, high temperature approach. This is exactly the same way as nature uses to compress carbon atoms very tightly. Well, in this case, what you have is huge press that is heated up to very, very high temperature. So the pressure that's applied is roughly one Eiffel Tower upside down on a little Coke can. That's a lot of pressure. And you cook it up at very high temperature, a lot higher than your oven at home. And then you turn graphite, you turn this guy into this, right? Sounds amazing. And actually, I have here some of these diamonds that are synthesized this way. This is diamond sand. There is about probably 20 carats of diamond, but it's not very valuable, so please don't run away with it. I'll ask Luca, maybe you can pass it around, give it to people so they can take a look at it. Okay, another way that scientists have developed to synthesize diamond that gives much purer diamonds is so-called chemical vapor deposition method, okay? In this case, what scientists do, they start with some substrate, could be a little bit of diamond, and then they bring in different atoms, different gases. In this case is CH4 gas, that then when dark balls are carbon atoms and white balls are hydrogen atoms. So what happens as these molecules of a gas come close to the surface, they get deposited and the structure grows. In fact, this was cartoon. If you don't believe me, you can take a look at our next slide that shows you, if you pay attention, the top layer is moving slowly up. This is diamond being grown in this chemical vapor deposition furnace, okay? So actually, using this method, people can grow diamonds of this size without any problem today. And, okay, so they can be very, very pure. They can be as good as natural diamonds, in some cases even better. But it's what's interesting, actually, that we are here, we're not so much interested in the pure diamonds, we are very much interested in impurities. Why? Because impurities can make diamond sparkle even better, have color, okay? So behind me is an example of a nice piece of jewelry from Museum of Natural History at Harvard, and what you see is brush, I guess that's the word. I'm not an expert in jewelry, but I sure know something about diamond. So here's golden setting, and there you can see a bunch of different pieces of diamond inside. What's interesting when you put this piece of diamond or this piece of jewelry under ultraviolet light, you see that it glows. Okay, so this is the same piece of jewelry that has diamonds, have nice, beautiful color. You put it under black light, and you can see all of these different colors coming out. There's a little bit of blue, there's a little bit of green, some violet, and so on and so forth. So what gives diamond these colors and what actually makes it glow so nicely are impurities. Okay, so people intentionally make diamond float, okay, by adding impurities to color them. For example, if I add a little bit of atom boron in my matrix of carbon, my diamond becomes blue. If I add some nitrogen, like the ones that are being passed around, they're yellow. Okay, and if I actually say have nitrogen and some defects, then diamonds become pink. And these pink diamonds are actually very expensive if they're natural, because they're very rare. Here we have example of pink quote-unquote diamond. Okay, this is a piece of glass, really. But here I have actual pink diamond. So, can you guys see it? But I'm going to show you that indeed these guys do glow. Do you see any red color coming out of it? So diamonds do glow, and it's actually this glow of diamond, these impurities in diamond, that make diamond so interesting. We are very much interested in these defects, and we would like to build some important communication systems out of them, as well as memory for computers. Before we go there, I'd like to introduce and explain to you how light gets emitted. So here's a very simple model of one nitrogen atom, just like this guy, but in free space, without diamond lattice. Atom has its core, its nucleus, and it has some few electrons around it. I focus here only on one electron. When I applied my green laser pointer, what I did, I added a kick of energy to this electron, and I promoted him to higher energy level. After some time, this electron that was excited decided to be de-excited and went back to its original energy and emitted red photon. So this is pretty cool. But what's really interesting and kind of unique to these impurities in diamond is that not only these atoms, these electrons can emit light, but they can store information. Electron can spin one way, and we call it spin 1. Just bear with me for a moment. Or it can spin the other way, and we call this spin 0. Spin up, spin down, okay? And it turns out that you can store information in the way which electron spins. Does it spin this way, or it spins that way, okay? You can use this as a memory. And this is very, very interesting, because you can, for example, encode this, as I mentioned, as 1, and this at 0. So what we need to do, we need to take our nitrogen friend and put it in diamond lattice, like so, like this one, okay? So here is nitrogen. We jammed it inside this carbon, and this carbon is now keeping this nitrogen in place. It's very tightly bound, and it cannot escape from carbon lattice. And what's really unique about diamond, that this cage of diamond, cage of carbon, does not disturb properties of this nitrogen atom a whole lot, okay? That's why it still maintains its emission properties, and it can be used as a memory. So this is sort of the punchline, is that nitrogen vacancy color centers in diamond can be used as atomic scale memory. Each of these little atoms is one memory site, which is way, way smaller than what you have today in your computers. What we would like to build out of these things, we would like to use a piece of synthetic diamond, like the one shown here, made a lot of these defects, okay? And then, like I show here in this pink array, and then these defects would be able to store information in spin up or spin down. Electron spin up or electron spin down means 1 or 0. And what's really cool is that I can come with my green laser, as I showed you earlier, and read this information simply because spin up emits a little bit less light, spins down emits a little bit more light, okay? So by shining light on diamond, I can read information. So this is how the basic component that you could use to build very dense memory that is based only on one atom, in this case nitrogen. But there is a problem, okay? As I told you earlier, diamond has very high refractive index, which really means it bends light very, very strongly. Basically, light that gets emitted in a diamond does not escape from diamond very easily. So this is the problem. I have my color centers, my nitrogen color centers, okay, in diamond. I would like to use them as a memory. In order to read that memory, I need to shine laser at it, and I need to collect some light that these guys are emitting. So this is what I need to do. The problem is, due to this diamond's ability to bend light, very little light comes out. So only about 3% of light comes down, so which means I have beautiful dense memory, but it's really, really slow. It takes me a long time to read it, okay? So that's not very good. So we would like to make very fast memories that are very, very dense as well. So solution to this would be really to just simply shave off the surfaces where these beams are hitting, the diamond surfaces where beams are hitting, as shown here. We would basically somehow like to remove this little bit of diamond, erode it away, okay? So what's left is this pillar, and now these yellow beams are not trapped anymore. They are actually guided, okay? They get this light now gets trapped inside this diamond pillar, and this can be used to transmit light very effectively towards the user, okay? So here's an illustration that shows, for example, on the right you have NV center in bulk that doesn't emit a whole lot, and in these pillars of diamond there are some color centers that emit quite a bit of light and are excellent memory. But the question is, so we knew that this could be done, we did some theory on it, but we didn't know how to make these devices, okay? So how do you etch, how do you remove the hardest material on Earth? That was actually quite a bit of challenge. How do you make something like this? So when we took inspiration from nature, and many of you may have seen these systems that are very impressive, eroded structures sculpted by nature over many, many, many thousands, millions of years. I don't want to say something incorrectly here geologically, but the way this is made is you have very hard material on top, some very solid rock, and then over the time, water and air keep eroding the soil around it, and what you have is this pillar. So this top layer masks the particular region underneath it, and the rest is washed away, and you have this nice pillar. Well, we figured out how to do exactly the same with diamond, okay? You can see these diamond pillars that we have made. They're very tiny. We put little rocks that are even smaller, roughly the size of virus, a little bigger than virus, these little rocks on top of the pillars, and then we eroded away diamond, okay? And what's left, only diamond underneath these rocks. And you can compare how good we are compared to nature. It took us about 1 minute to make these things. Nature took many, many, many years, okay? Ours are much smaller, roughly 1 micron tall, whereas natural systems are on the order of, I guesstimated 100 meters. I'm not an expert on this. So our structures are about 100 million times smaller than what nature does. And they have very different function, very different purpose. The purpose of our devices is to trap light emitting for our defects, our nitrogen defects in diamond, these impurities, and collect it somehow from both top and bottom. And when this is done, basically what we can finally start dreaming about using this technology to start building some very interesting memory elements. Here is one array. This is cartoon. We have demonstrated this experimentally as well. I'm not showing you this data. What we have here, we have diamond substrates. There are some on display downstairs. You can see them. By the way, maybe I can show you here. These are some of these artificial diamond substrate that we use. These are pretty big. You can build serious memory elements in it. We'll use these large pieces of diamond, fabricate devices in it, and then some of them, they have these color centers I was talking about, these impurities, and we can store information in them. For example, I stored one in these diamond pillars that are glowing. And the way we did it, actually, an experiment is very cool. We not only use diamond, we use silver, sometimes even gold, to use it as a mirror. Okay, silver is a very nice mirror, as you probably know, because every morning when you wake up, perhaps you look at a mirror in your bathroom. Well, actually, the silver layers around diamond can reflect light and helps us get even more light out of these impurities. Okay, so we made very tiny mirror and very tiny pillars of diamond, which helped us make very dense memory. After many years, after my students have been working diligently in the lab, This is sort of the result. Millions of diamond nanowires fabricated in single crystal diamond substrate, and that allows us to collect light from them very, very effectively. And now we are exploring various applications. For example, one application that I mentioned originally is secure communication. Perhaps you're aware, if you have Fios internet at home, maybe, then certainly know that when you watch movies, these movies come to you home through optical fibers. So optical communication is dominant technique, dominant approach to communicate a lot of information very, very effectively. But the problem with optical communication, the way this works roughly is you have basically at one end you have laser, and the laser gets turned on and off like so. On means 1, bit information 1, off means bit of information 0, 1, 0, 1, 1, 1, 0. And this is how you can communicate over long distance. But the problem is if somebody wants to listen to your communication and spy on you, they just need to take a little bit of light out, and you will never notice this, and they can get access to your information. However, if you use defects in diamond, they emit 1 photon at a time, as illustrated above me, 1 particle of light at a time. So if somebody steals it away from you, you know immediately that something's wrong, and you stop your communication channel. This is of great interest for Department of Defense, to private communication, security, to banks and whatnot. So this is one possible application. All right, so hopefully I convinced you so far that diamond is not only girls' best friend, but it has many interesting properties, and I certainly like it, and many of my colleagues who are engineers and scientists like it a lot, and hopefully next time you see diamond ring, you'll think how to damage it, make some wires in it, and whatnot. I don't encourage you to do that. It can be expensive. All right, so with that, I'd like to thank you. I'd like to thank people who supported this presentation, in particular Center for Integrated Quantum Materials at Harvard, as well as my department, School of Engineering and Applied Sciences at Harvard, and Center for Nanoscale Systems, which is big clean room where we make these devices. Also, I'd like to acknowledge my students who did most of the work that I showed to you. So thank you very much, and I'm happy to take any questions that you have.